Good morning, students. So in the last class we have completed the discussion on the Laplace transform of unit impulse function. Now today in today's class we'll be actually discussing on the Laplace transform of the Dirac-Delta function, also known by the name impulse function, and also the Laplace transform of some special functions. Now before I start with the definition of the Laplace transform of impulse function, I define what is an impulse. Now, in applied mechanics, an impulse is said to be a large force that acts for a short time. Now, when a large force acts for a small time, very small infinitesimal time, then the product of the force and the time is called impulse in applied mechanics. Okay. Now, the unit impulse function is the limiting function which is normally denoted by delta t minus 1. So we define the unit impulse function as delta t minus 1 is equal to 1 by epsilon from a, for t varying from a to a plus epsilon and is equal to 0 otherwise. So if you look at the graph of this function that I have written here, we will get a graph something like this. You see, I have taken on the x-axis the time, and on the y-axis I have taken the function. So you see, from a to a plus epsilon, okay, a to a plus epsilon, the function is delta t minus 1 is equal to 1 by epsilon, right? So it's a straight line parallel to x-axis. The height is, the magnitude is 1 by epsilon, clearly over here. Now it is very easy to see that when epsilon becomes 0, because epsilon is a very small quantity, however small you can think, if epsilon tends to 0 in the limiting sense, then it is easy to see that 1 by epsilon tends to infinity, which means that the value of the function becomes infinite as epsilon tends to 0, and in that process the area of the rectangle becomes unity. So in that case, the unit impulse function is defined as follows. It is defined in this manner: with respect to a particular point A, delta t minus a will be equal to infinite for t equal to a and will be equal to 0 for t not equal to a, because in the previous definition from a to a plus epsilon, if you make epsilon tends to 0, then t becomes equal to a, where the value of the function becomes infinite, right? So delta t minus a will be infinity for t equal to a and will be equal to 0 for t not equal to a. And since the whole area of the strip, rectangular strip, is unity, so if we integrate this unit impulse function delta t minus a from 0 to infinity, the whole area will be equal to 1. Okay, so because the area of the strip is equal to 1, which is unity. So this is a very important thing which you must remember. Now, having said this, we now come to a very important theorem of unit impulse function, which is called the filtering property of unit impulse function. The filtering property of unit impulse function and its Laplace transform. How to find the Laplace transform of a unit impulse function. Now, first we state that what is this filtering property. So suppose we consider that ft be a continuous and integrable function in 0 to infinity. Then if we take the integral from 0 to infinity ft into delta t minus a dt, this integral will be equal to the value of the function at the point a, that is f of a. This is called the filtering property of the unit impulse function. And if you use this property, you can find out also the Laplace transform of unit impulse function. Okay, so what is that? So it is L of delta t minus a will be equal to e to the power minus s. Now let's come to the proof of this statement, because we have stated that this is the property that will hold. Now there must be a proof behind it. So we go to the proof of this important theorem. So we start from the definition. We have integral 0 to infinity ft delta t minus a dt, right? Now we have to show this equal to fa. Now by definition of unit impulse function, okay, 0 to infinity ft delta t minus a dt will be equal to integral a to a plus epsilon 1 by epsilon into ft dt, because delta t minus a is equal to 1 by epsilon from t a to a plus epsilon, right? Now, if we use the mean value theorem of integral calculus on this integral, what we obtain? So, using the mean value theorem of integral calculus, we obtain this integral 0 to infinity ft delta t minus a dt becomes equal to, which we wrote earlier, a to a plus epsilon 1 by epsilon into ft dt. Now, that will be equal to 1 by epsilon being a constant, it will go outside. It will be into f t0, where t0 will be a value lying in the interval a to a plus epsilon into the integral a to a plus epsilon dt. Okay, so if you integrate dt from a to a plus epsilon, it will be t, and then if you put the limits, upper limit minus lower limit, so it's a plus epsilon minus a. So a plus epsilon minus a is epsilon, so that epsilon will cancel with the denominator, and hence the result will be ft0. So we get the integral 0 to infinity ft delta t minus a dt will be equal to ft0, where t0 is a value lying in the enclosed interval a and a plus epsilon. Now what we do is that we make epsilon tends to 0. So if we take the limit of on both sides as epsilon tends to 0 plus, so what we get? So on the right hand side we get limit ft0 epsilon tends to 0 plus, and that will actually be equal to f of a. Why? Because t0 is lying between a and a plus epsilon. So if you make epsilon tends to 0, t0 will coincide with the point a, and hence it will converge towards the value of the function fa. So that's the way we prove the filtering property of the unit impulse function. So therefore I can say integral 0 to infinity ft delta t minus a dt is equal to fa. Now if we take ft, having proved this, now we are taking the result of this to prove the Laplace transform of the unit impulse function or the Dirac-Delta function. So if we take in place of ft e to the power minus st, then what do we get? We'll get something like this. We'll get integral 0 to infinity e to the power minus st into delta t minus a dt. Just in place of ft, we are putting the value of e to the power minus st. Now if you put that, and if you use the filtering property, then by definition of the filtering property it should be e to the power minus s, because it says that integral 0 to infinity ft delta t minus a dt will be equal to fa. So in place of ft, if I write e to the power minus st, so in place of t I will just write the value a, so it will be e to the power minus s. So now what is the left hand side? The left hand side, as you see in this equation, is actually L of delta t minus a, the Laplace transform of delta t minus a, and on the right hand side it is the result. That means the Laplace transform of the unit impulse function or the Dirac-Delta function is e to the power minus s. Okay, so this is a very important result as far as the Dirac-Delta function or the unit impulse function is concerned. So is it clear? I hope you have understood the definition of a unit impulse function and its filtering property, and using the filtering property how we are evaluating the Laplace transform of a unit impulse function. Now coming to one example, very simple example though, I just say that let's say you are asked to evaluate the Laplace transform of 1 by t into delta t minus a. Now you all know, just now we did, the Laplace transform of delta t minus a is e to the power minus s, right? We just now did. So we already did a property called division by t, if you remember. So if we apply the division by t property, so because we already know Laplace transform of delta t minus a, which is e to the power minus s, that is, let's say that's equal to f bar s. So from the division by t property, if you remember, L of ft by t will be integral s to infinity f bar s ds. So exactly I am doing it over here. So L of delta t minus a by t, which is asked in the question, will be equal to integral s to infinity e to the power minus s into ds, right? So which on integration gives me e to the power minus s divided by minus a. The limits are from s to infinity. We are assuming the fact that both a and s are positive, because if a and s are not positive, this integral will not converge, it will diverge. If any one of them is negative, let's say if a is negative, then we get a e to the power some positive quantity. So in that case, it will diverge to plus infinity. So a and s must be positive for its convergence, and ultimately we get the result to be e to the power minus s by a. So that's the answer of this particular question. Clear? Now coming to the second example, we see that evaluate integral 0 to infinity sine 2t delta t minus pi by 4 dt, right? So in this case, what we do is that we first assume that the function ft be equal to sine t. Okay, so if we assume ft equal to sine t, we know the filtering property. So if we use the filtering property, integral 0 to infinity sine 2t into delta t minus a dt, what should we be getting? We should be getting f of a. F of a means sine of twice a in this case, because ft has been assumed to be sine t already. So we are getting sine 2a. So I can write integral 0 to infinity sine 2t delta t minus a dt is sine 2a. But here the question is delta t minus pi by 4. So that means your a here is nothing but pi by 4. So if I put a equal to pi by 4 in this particular equation, then I'll be getting the answer, and that's what exactly I'm doing over here. So I'll just put the value of a equal to pi by 4 and I'll be getting the answer to my question. That is integral 0 to infinity sine 2t delta t minus pi by 4 dt will be equal to sine of 2 into pi by 4, that is sine of pi by 2, which is all we know is equal to 1. So the value of this integral becomes equal to 1. So we have evaluated an improper integral using the unit impulse function or the Dirac-Delta function. So I hope you have understood these two problems related to the unit impulse function. Now having done that, now we come to the Laplace transform of some special functions. Now special function, now there are some functions in calculus which are special functions, we call it. Now as far as the syllabus is concerned, we will be dealing with three such special types of function. One is called the Bessel function, then the second one is called the error function, and the third one is called the Laguerre polynomial. Okay, so one by one we will try to find out the Laplace transform of each of these three functions. First we come to the Laplace transform of Bessel functions, that is of order 0 and order 1, that is known by the name J0x and J1x. Now this part I think you have not covered in your previous semester, because I tell you, basically I just give you an idea. These Bessel functions are basically nothing but a series solution of the Bessel's equation of second order. We have in differential equation a differential equation which is called Bessel's equation, okay, which is of the second order, and the solution of the Bessel's equation gives rise to Bessel's function of order n, that is Jnx. Now in this case, we'll be actually trying to find out the Laplace transform of the Bessel function of order 0 and order 1. Okay, now we know from the definition of the Bessel function of order 0, J0x is given by this. It is given by, as I told you, it's a series solution. The solution will be in the form of a power series, right? So you can see it over here. The J0x is written in the form of a infinite series, right? So the form of J0x, which you have to remember because you have not gone through this particular section before, is given by 1 minus x square by 2 square plus x to the power 4 by 2 square into 4 square, and like that, minus x to the power 6 by 2 square into 4 square into 6 square, and plus dot 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 up to infinity. Now if I want to find the Laplace transform of J0x, so I just simply take Laplace transform on both sides. So I take Laplace transform of J0x. So if I do that and apply the linearity property, so I take Laplace transform of each of these terms on the right one by one. So first I take Laplace transform of 1 because the first term is 1. So Laplace transform of 1 is 1 by s. So I've got 1 by s as my first term. You see? Secondly, I take the Laplace transform of x square because minus 1 by 2 square is a constant that is taken outside. So Laplace transform of x square is 2 factorial by s to the power 2 plus 1. Like we know Laplace transform of t to the power n is n factorial by s to the power n plus 1. So n is 2, so it's 2 factorial by s cube. In this case 2 plus 1 is 3, so s cube. In a very similar manner, we go on to find out the Laplace transform of the remaining terms. Like in next case it was s to the power 4, so it will be 4 factorial by s to the power 4 plus 1, which is 5. Okay, and like this we go on finding out for the remaining terms right up to infinity. After having found out those things, I take 1 by s common, because you see 1 by s can be taken common from all the terms. So if you take 1 by s common from all the terms, you are getting 1 minus half. You'll get an expression something like this: 1 minus half into 1 by s square plus 1 into 3 by 2 into 4 into 1 by s to the power 4 minus 1 into 3 into 5 by 2 into 4 into 6 into 1 by s to the power 6 plus dot 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 right up to infinity, because it's an infinite series, because it's series solution, Bessel's function of order 0. Now this expression that you have got in the second bracket can be written in a binomial expansion, binomial theorem. We can use the binomial theorem and write this in the form of 1 plus 1 by s square whole to the power minus half. We can do that. So if I, because you see 1 plus 1 by s square whole to the power minus half, if you expand it, you will exactly get the same expression that you have got in the previous step within the second bracket. So after simplifying it, you will ultimately get the result to be 1 by square root of s square plus 1. So that is the Laplace transform of Bessel's function of order 0, that is J0x. Now I have told you in my earlier classes that there is a property called change of scale property. Remember? What was the property? I have written that again here. That if you know Laplace transform of function of ft is known to be equal to f bar s, then you can find the Laplace transform of f(at), and that will be nothing but 1 by a into f bar s by a. That means the scale of the function is changed. Okay, scale of the variables change, and so we'll get something f bar s by a. If you put a equal to 1, you get back the basic definition of Laplace transform, because when a is 1, there is no change of scale, right? So a similar thing can be applied over here for J0x in place of J0x or J0t as you call it. So if I say I want to find out the Laplace transform of J0at or any constant multiplied by t, then I can easily do it. I'm going to apply this particular theorem of the change of scale property, and I'll be getting 1 by a into 1 by square root of a square by a square plus 1. Okay, so in place of s, I'm just replacing s by a. I'm multiplying 1 by a outside, so I'll be getting something like this, which on simplification becomes 1 by square root of s square plus a square. So remember the result, L of J0at is 1 by square root of s square plus s. Let's say L of J03t will be 1 by square root of s square plus 9, right? So like that. Now let's come to finding out the Laplace transform of the Bessel's function of order 1, which is also in your syllabus. Now how we can obtain that? We can obtain that very easily from the result obtained just now for Bessel's functions of order 0. Because in Bessel's function of order 0 and Bessel's function of order 1 maintains a particular relation. What is the relation? The relation is J0-x is equal to minus J1x. These things are all there in the series solution of ordinary differential equation, a thing which is not in your syllabus right now. So for the time being, you must remember these results in order to answer question from this particular section. So remember this result that J0-x is equal to minus J1x. So if you know that, then you can easily find out L of J1x. So what I'm doing is that from that relation, I am just taking the Laplace transform on both sides. If I take the Laplace transform on both sides and interchange the minus side on this side, I get L of J1x to be equal to minus L of J0-x. There's no doubt about that, right? I just take L on both sides, Laplace transform on both sides. So L of J0-x is, from the definition of the Laplace transform derivative, it is s into L J0x minus J00. If you remember, L of f dash t was said to be s f bar s minus f0. So a very similar thing. So L of J0-x will be s L J0x minus J00, right? Now L of J0x has just now been obtained. We just obtained it to be equal to 1 by square root of s square plus 1. So it will be s into 1 by square root of s square plus 1 and minus 1. Why? Because J00 is 1. That's a known result. That is a known result from the Bessel's function chapter. So we have used this result over here. Then we'll observe this minus sign and finally get a result like this. 1 minus s by square root of x square plus 1 is the Laplace transform of the Bessel's function of order 1. Clear? Okay. Now coming into the Laplace transform of the error function, another special type. We have done the Bessel's function, now we'll come to the error function. Now what is error function? First of all, we define what is error function. This error function, I don't know how many of you have done statistics, particularly the Gaussian normal distribution. And there you'll find this application of error function is there. So an error function, those who have not done, please just remember this definition here. Error function normally denoted by ERF, okay? ER stands for error, F stands for function, of root of x is defined to be 2 by root pi integral 0 to root x e to the power minus t squared dt, okay? Now we need to find out the Laplace transform of this error function ERF. Now how do we do it? We do it very simply by first expanding that exponential series. We'll keep everything same, just expand e to the power minus t square in exponential series, which we can easily do, and we will do that, and we have done that. So it will be 2 by root pi integral 0 to root x, and if you expand in an exponential series, you will get 1 minus t square by factorial 1, which I have not written, factorial 1 is 1, plus t to the power 4, that's t square whole square by factorial 2, minus t square whole cube, that is t to the power 6 by factorial 3, and so on, so on. Okay, dt. Now, objective is to find the Laplace transform of this. So, what I do is that I now take the Laplace transform of this function. Before I take the Laplace transform function, I put the upper limit minus the lower limit. I use the fundamental theorem because I have expanded e to the power minus t square in an exponential series. I'll just integrate this one. It's a very simple integration. It's a polynomial function now. So I'll just integrate term by term. So it will be t cube by 3 like that. So I'll integrate it. I'll put the upper limit and lower limit. After putting the upper limit and the lower limit using the fundamental theorem, I will get something like this. It will be a function of x obviously because it is 0 to root over x, the limits are. So I'll get 2 by root pi into x to the power half minus x to the power 3 by 2 by 3 plus x to the power 5 by 2 by 5 into 2 factorial minus x to the power 7 by 2 by 7 into 3 factorial plus dot 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 and so on. Now we are in a position to take the Laplace transform of this error function. So if we take the Laplace transform of the error function root over x, ERF root x, we'll do in the same manner as we did in case of the Bessel function. What we'll do? We will basically take the Laplace transform of each and every term by term. From the linearity property we know that. So it will be 2 by root pi, and then we come to the first term. So L of root over x, that is x to the power half. So remember, I told you the Laplace transform of some standard functions. Laplace transform of t to the power n, I told you. I told you that when n is a natural number or a positive integer, it is n factorial by s to the power n plus 1. But if n is greater than minus 1, okay, then also you can write that in the form of a gamma function. That is gamma n plus 1 by s to the power n plus 1. So that same case has arisen over here. So L of x to the power half will be actually equal to gamma half plus 1 divided by s to the power half plus 1. So gamma half plus 1 is gamma 3 by 2 and s to the power half plus 1 is s to the power 3 by 2. So that's the explanation of the first term, that why we have got gamma 3 by 2 divided by s to the power 3 by 2. Okay. Next term is Laplace transform x to the power 3 by 2. You see, in the same manner you can do it. So it will be gamma 3 by 2 plus 1 divided by s to the power 3 by 2 plus 1. Because it's gamma n plus 1 by s to the power n plus 1. So gamma 3 by 2 plus 1 is gamma 5 by 2 divided by 3 was already there into s to the power 5 by 2. And in this way, I go on finding out for the remaining terms. Like in the next case, x to the power 5 by 2, this will be gamma 5 by 2 plus 1 divided by s to the power 5 by 2 plus 1. That means gamma 7 by 2 divided by 5 into 2 factorial was a constant into s to the power 7 by 2. Similarly, we'll get minus gamma 9 by 2 divided by 7 into 3 factorial and s to the power 9 by, and so on we will get for all the remaining terms right up to infinity. Now gamma 3 by 2 Now what is gamma 3 by 2? Now gamma 3 by 2 you can write as gamma half plus 1. Now gamma half plus 1 from the property of gamma function, which you did in the last semester, is half gamma half, because gamma n plus 1 is n gamma n, right? So I use that result over here, half gamma half. Now gamma half is root pi, okay, right? So I just write in place of gamma 3 by 2, gamma half plus 1, which I write as half gamma half. Replace gamma half by root pi. That root pi will cancel, half will also cancel, and therefore I'll get the term to be only 1 by s to the power 3 by 2, which you see I have got it over here, right? Next is gamma 5 by 2. Now how to get gamma 5 by 2? Now gamma 5 by 2 will be first written as gamma 3 by 2 plus 1. Now gamma 3 by 2 plus 1 is 3 by 2 gamma 3 by 2. Then again gamma 3 by 2 is gamma half plus 1, which is again half gamma half, which means gamma 5 by 2 is 3 by 2 into half into gamma half. Again gamma half comes, so gamma half is root pi. That root pi cancels with the denominator, and the leftover constant terms are left. Simplification is done, and we get a term. You'll get the same term, minus half into 1 by s to the power 5 by 2. Similarly, for gamma 7 by 2, we first write gamma 5 by 2 plus 1. That means 5 by 2 gamma 5 by 2. Then break gamma 5 by 2 into gamma 3 by 2 plus 1. That is 3 by 2 gamma 3 by 2. Then break gamma 3 by 2 as gamma half plus 1. That is half gamma half. That means it is 5 by 2 into 3 by 2 into half into gamma half. Gamma half being root pi. The root pi cancels with the denominator because root pi was outside the bracket, and the constants are left behind, which on simplification gives me something like this: 1 by 2 into 3 by 4 into 1 by s to the power 7 by 2. So in this way I find out the next term, and so on right up to infinity. After having found out all these terms, that is after having found out the Laplace transform of all these terms term by term, we now take 1 by s to the power 3 by 2 common. You see, we can take easily 1 by s to the power 3 by 2 common from all the terms. If you do that, you will see the first term is 1, of course, because 1 by s to the power 3 by 2 was the only term, was taken common from the first term. So my second term becomes minus half into 1 by s, because you have taken 1 by s to the power 3 by 2 common. Third term becomes half into 3 by 4 into 1 by s square. My fourth term becomes minus half into 3 by 4 into 5 by 6 into 1 by s cube. So in this way, it goes like up to infinity. Now what about this expression within the second bracket? The expression within the second bracket can be again represented in the form of a binomial expansion. We can write this as 1 plus 1 by s to the power minus half. Please check. Because if you expand 1 plus 1 by s to the power minus half binomially, you should be getting the expression which I have written in the second bracket. Okay. So I replace this entire expression of second bracket with this binomial by using the binomial theorem. So I just replace it by 1 plus 1 by s to the power minus half, which on simplification gives me 1 by s into square root of s plus 1. Okay. So that gives me the Laplace transform of our error function. That is the result you must always remember. The results is very important. If you don't remember the proofs, remember the results. The proofs are also very important. Proofs will come. And results are of course very important, because otherwise you will not be able to do anything actually. At least you will be able to do the problems, at least the MCQ problems or the subjective questions that might come from this particular section. The results you must be knowing it thoroughly at the time of exam. Now coming on to the third and the final function, special function that we have, that is the Laguerre polynomials. Laguerre polynomials, a very well-known polynomials, which is actually nothing but a solution again of the second order Laguerre differential equation, which also you have not done. But just remember for the time being that the solution of Laguerre equation, okay, gives you or gives rise to a Laguerre polynomial, which is also a series solution of this differential equation. So a Laguerre function, Laguerre polynomial is denoted by normally by ln x, and it is given by this. Remember this result: e to the power x into the nth derivative with respect to x of the function x to the power n into e to the power minus x. That is the Laguerre polynomial ln x. Now I want to find out the Laplace transform of this Laguerre polynomial. So if I want to find that, I take Laplace transform on both sides, and you see, as we take the Laplace transform from the definition of Laplace transform, this will be integral 0 to infinity e to the power minus st into the function, that is the e to the power t into dn dtn t to the into t to the power n e to the power minus t dt. I just replace x by t because normally it's a time variable. Now we make a simple modification using the laws of indices. We write e to the power minus st into e to the power t as e to the power minus s minus 1 into t, and then the rest of the thing remains same, that is the nth derivative of with respect to t of the function e to the power minus t to the power n. Then we integrate by parts. Now while integrating by parts, I take the exponential function as my first function and the other function, that is dn dtn of e to the power minus t into t to the power n, as my second function. So if we take e to the power minus s minus 1 t as your first function and the other one as the second function, you should get, if you apply the rules of integration by parts, which you very well know, it will be e to the power minus s minus 1 t into integral of dn dtn of e to the power minus t into t to the power n dt. So which will give me dn minus 1 dtn minus 1 of e to the power minus t into t to the power n. I put the limits from 0 to infinity, which I'll evaluate later on. Now coming to the other part of the integration by parts, plus integral ddt of e to the power minus s minus 1 t, which is e to the power minus s minus 1 t into s minus 1. That minus and minus will make it plus. That's why we have plus outside the integral. And integral of dn dtn of e to the power minus t to the power n is dn minus 1 by dtn minus 1 e to the power minus t to the power n. So we are getting e to the power minus s minus 1 t into s minus 1 into dn minus 1 by dtn minus 1 of e to the power minus t to the power n dt and nothing else. Right? Now if you look at the first term, you see the first term vanishes in both the limits. We are assuming the fact here that s is greater than 1. If s is not greater than, that means s minus 1 is positive. Because if s minus 1 is not positive, then it will not converge. It will diverge in fact, because s minus 1 is negative, then it will diverge at infinity, so therefore that thing is not to be considered. So assuming s minus 1 to be positive, that means s is greater than 1, we'll find that the upper limit is also 0 and the lower limit is also 0, because the moment you put t equal to 0, it's 0. So the first term vanishes in both the limits. Now coming to, so we are left with the second term only. So we take s minus 1 outside the integral, which we did in the very next step, you see right over there, and we are left with the other terms in the integral, e to the power minus s minus 1 t into dn minus 1 dtn minus 1 e to the power minus t into t to the power n dt. Okay, again we integrate by parts. If we integrate by part again, in fact we have to integrate by part n minus 1 times, and you'll get a very similar result because of the fact that there's exponential function over here. So things are pretty easy for you. So if you do it because unless you do n minus 1 times, you won't be able to get rid of this derivative over here. So on doing that, you will get s minus 1 to the power n, because you have done it n minus 1 times. For n minus 1 times, for each one of those n minus 1 times, s minus 1 will come. So it will make it s minus 1 was already there, 1 outside, into s minus 1 to the power n minus 1, which will make it s minus 1 to the power n. And we will be left with integral 0 to infinity e to the power minus s minus 1 into t into e to the power minus t into t to the power n dt, because the derivative will be off by then, because you have already differentiated n times, actually n minus 1 times after the first one. So eventually you have done it n times, right? You will get something like this. Okay, so you are getting s minus 1 to the power n into integral 0 to infinity e to the power minus s minus 1 into t into e to the power minus t into t to the power n dt. Now you see e to the power t, we get e to the power plus t into e to the power minus t, that means e to the power 0, which is 1. So we are left with s minus 1 into the power n integral 0 to infinity e to the power minus st into t to the power n dt. Now what is this? this is Laplace transform of t to the power n. The integral, I'm talking of the integral, this one, I'm talking of this integral right over here. Integral 0 to infinity e to the power minus st into t to the power n dt is nothing but Laplace transform of t to the power n. So it's Laplace transform of t to the power n, right? So we finally get s minus 1 to the power n into Laplace transform of t to the power n. And Laplace transform of t to the power n, all of you know, the result is n factorial by s to the power n plus 1. So we put that value over here and we eventually get s minus 1 to the power n into n factorial by s to the power n plus 1. So finally the result becomes Laplace transform of the Laguerre polynomial ln x turns out to be n factorial into s minus 1 to the power n divided by s to the power n plus 1. But mind it, s must be greater than 1, because if s is not greater than 1, this integral will not converge. It will diverge in that particular case. So hope you have understood today's lecture. So with that I come to the end of today's class. In next class we will discuss more topics on Laplace transform. Thank you very much.